Good evening. Welcome to this keynote session. My good friend Jaideep has been woken up early to give a talk to us. So because of the hybrid mode, Professor Jaideep Vaidya is a distinguished professor in the MSIS department of Rutgers University, and he is an alumnus of University of Mumbai and has a MS and PhD from Purdue University. His general area of interest has been data mining, data management, security, and privacy, and he has won several best paper awards, nearly 130 technical papers, and he is received the NSF Career Award, Rutgers Board of Trustees Research Fellowship for Scholarly Excellence, and Junior Faculty Award from Rutgers Business School. He is also, I think in my opinion, he is a fellow of IEEE and has been recognized as an ACM distinguished scientist. And then Jaideep can correct if I have done a mistake. And also I think we worked together on running a ICIS couple of years back at Bombay. Jaideep, your time.
Sir, your audio, we are not able to hear. I think you are muted.
Can you hear me now?
No. Yes, sir. Yes, sir, you are audible now.
Okay. All right. Perfect. Yeah, so again, thank you, Professor Shamsundar, for that kind introduction. I'm really happy to be here today, unfortunately, virtually, not in person. I was in India just last month, but unfortunately, the semester has now started over here, so I had to return back to the US. So let me get started. I mean, after that really interesting discussion, to something a little bit more pedantic, but something, that is related to sort of the applications of public key infrastructures and general security infrastructures that we have, where we sort of see the field going ahead in I would say, the next decade or so. And there is a sort of lot of interest in this, but I'll get into this general area of privacy preserving data sharing and analytics, some of the challenges that are there, and some of the things that sort of need to be done in this space as well. But again, thank you for this opportunity. If you have questions, please feel free to stop me at any point of time, and I would be more than happy to sort of answer those. So before I get started, the customary acknowledgements, quite a bit of the work that I'm talking about in this was funded by the National Science Foundation, by the National Institutes of Health, and the National Academies of Sciences in the US. And of course, none of this work would have been possible without my collaborators and students. The list below is very, very incomplete, but refers to the people whose work I'm in particular going to talk about a bit. So again, why are we interested in this notion of data sharing and analytics? Simply because we have a large quantity of data today. There's this huge promise of big data and AI/ML, vast amount of information being created, very little of it actually which is being analyzed and sort of used. And for every organization, indeed every country, we really need to sort of make use of this big data or AI/ML technologies, because they have this potential to revolutionize innovation, competition, and productivity. And I just wanted to give you three very sort of obvious examples, if you will. But for example, in the healthcare sector, and we have specific figures for the US healthcare sector, use of these technologies would lead to sort of cost savings of over $300 billion a year, reduce healthcare expenditure by 8%, but more importantly, through personalized medicine, basically provide you better quality of life, better personalized treatments as well. Similarly, in the public sector administration, again, region, if you will, there can be a huge increase in productivity and again cost savings. For example, in the Europe public sector administration, the expectation is that it will save over 250 billion euros a year as well. And as we see in countries like India, other developing countries as well, this is even more important, because essentially we need to make use of all of the resources that we actually have. And this not only increases trust, but increases productivity as a whole. And the third and final example is just the US retail sector, which I'm not going to really go into, but of course there is improvement in productivity, but also in net margins that are possible through the use of these technologies. Okay, fantastic. So we have data, we really should use it, and we would be able to sort of realize great gains in a lot of different things. So what's the problem, right? Where is the rub? And the problem that we see, the peril, if you will, is that typically there is insufficient in-house capabilities or expertise for ingesting this data, for longer-term storage, for computation, for analytics. But more importantly, much of this data is actually sensitive, and at least in the short term, if not the long term, if you will, and there is this threat to privacy and security. So there's the threat to individual privacy. If you remember what happened, for example, with the information that is being collected through Aadhaar, and the data breaches that have happened in that space as well. But at a organizational level, there is also competitive advantage to be gained from information. And again, simply sort of having these global registries or simply going ahead and sharing this information can be problematic, either in terms of violating regulatory or confidentiality laws, or in terms of what use you can make out of this information. You can use it in ways that were very unanticipated and do fairly bad things as a result of this. So often data is strictly controlled, which is a good thing. But the bad thing is that it's stuck in silos, as it should not be, and it cannot actually be used. So just to sort of hammer the point home, because people may ask, what does it matter, right? I mean, a lot of data about me is already out there. Is there really this threat to privacy, and security? Is it really a big problem? What can you know from data? A huge number of things, as it turns out, right? So there have been attacks over attacks and all sorts of unexpected things. Human beings are very ingenious, if you will. So for example, even from the last name, from the surname, we are able to identify personal genomes, which is pretty surprising. Or you can identify participation in complex DNA mixtures, or I can look at your EEG data and so on and leak financial and identity related information. I can model the facial shape from DNA or participation from summary statistics, even something as simple as putting in reviews for Netflix, which Netflix doesn't allow anymore, but it used to. But let's say Netflix reviews or Amazon Prime reviews, you can link things back to IMDb and you can identify users. And indeed, you can even identify complete patient's information from aggregate and anonymized queries. This is something that, in fact, we did a few years ago. But all of these things are easily possible. And more attacks are sort of being developed, which essentially say, hey, you know what, just going ahead and thinking that, you can't use data in bad ways is absolutely not true. So the list goes on and on. And often the first solution, especially from a governmental perspective, but in general that people rise to is just to say, oh, why don't I just aggregate data? Let's not worry. We are not revealing individual data points. Is that good enough? And remember, we are not just talking about things like encryption. Of course, you need encryption for data at rest. But when you're computing over data, especially when you're revealing the results over this, the question is, can I just aggregate and is that good enough? And of course, the answer for that is no as well. And one, super small snapshot that I just wanted to sort of briefly talk about. This is some work we did in 2013. It got the Distinguished Paper Award from the American Medical Informatics Association. We basically were able to run a bunch of queries against this very well-known and publicly accessible data sets called HCAP, which is the Healthcare Cost Utilization Project. It basically captures data from all of the hospitals in all of the 50 states in the US and makes it available in aggregation. So you can run sort of queries which are aggregate queries. You basically get contingency tables categorized by different sort of things. So in this case, for example, we were asking how many women had ovarian, or how many people had ovarian cancer, and can we classify that by age and by race and ethnicity? And the stuff that you see in yellow is everything that has been suppressed. This is aggregate information, things have been suppressed. but actually you can run branch and bound sort of algorithms for inference, and you can just run queries against this. And we essentially found that, it was in this case one particular Native American woman who went to a privately owned hospital, who was exactly 75, did not pay by private insurance, stayed in the hospital for 34 days. And we even know how much she had to pay for this treatment and things like that. So again, just aggregation by itself clearly is not a solution. We need to go well beyond that, so to speak. So the question is, what can we do? And we want to link that back to sort of the infrastructures that we have, like public key infrastructures, and can we sort of create supporting infrastructure for what we want to sort of do? So again, we need to understand the data. We need to understand the usage. What is it that you need to do with this data? And then match the techniques to the required tasks. And from a privacy perspective, what you really need to do is ensure sort of three things. First is ensure process privacy, which means that whatever you're computing, the process of that computation should not be leaking any additional information, so to speak. The second is we want to ensure output privacy, which means that if you learn the result of this computation, then the result by itself should not be leaking any additional information. And I'll come and talk about this in just a minute. And finally, you want to ensure sort of control over the data used in this space as well. So every party, not just the individual, but organization, should be able to precisely control what data is used for what purposes in any given computation. So again, protecting the process. People here may be aware of this already, but there is a huge field or subfield of cryptography called secure multi-party computation, which basically enables this. Okay, and the idea is that, okay, if you have any function f and sort of n inputs, x1 through xn, which are distributed at those n different sites, we somehow want to compute this result y, which is the function f applied over x1 through xn, while revealing nothing to any site except its own input and the result. So every site should, of course, it knows its own input, it would get the result. And the reason why nothing is starred is that, of course, you're allowed to learn something more. Anything you can infer from the result and from your own input is fine, because that you would get in sort of in any case, even if there was a trusted third party to sort of do this. So this, the great news, this is a subfield of cryptography which has been around from the 1980s. One of the biggest sort of advances was to show that, hey, this is actually possible. Andrew Yao first showed that with the Yao's millionaire problem, that secure computation is possible if the function can be represented as a circuit. And the idea was simply securely compute each gate of the circuit and continue to sort of evaluate the circuit as well. And again, this was a, in some sense, the word seminal is really overused. So I will call it an earth-shaking result, because we know, theoretically speaking, that any computation that you would carry out on a computer can be represented as a circuit. And therefore, in theory, what this means is that anything that you want to do can be done in a fully distributed way, wherein you would learn nothing, so to speak, beyond your input and final output. And it was extended not just to, from two parties to multiple parties as well. So this has been around for now close to 40 years. So what's the problem? The biggest problem has been that, yes, this shows in theory that everything is possible, but in practice, there is this huge problem of efficiency. Because if you think of representing the computation as a circuit, and we are really talking about a Boolean circuit, you would have a huge circuit. And essentially, when you're talking about analysis over large quantities of data, this becomes even worse. I mean, this creates when the input data size is huge, you have this huge problem with sort of efficiency, which basically means that you can't just directly go and sort of do this. The good news is that recent work has made a lot of complicated analysis actually feasible. And I have some links over there. You are welcome to look at those. Slowly, we are maturing to the point where this could actually be provided as sort of pieces of software, and sort of general analysis tasks can be carried out with techniques of this kind. But that's great, because again, What we need is infrastructure in order to do this that is already out there. And I'll come back to that in just a few minutes as well. The second part of the puzzle is protecting the output. And for this, for the most part, we can use something like differential privacy. And for those of you who have not been exposed to differential privacy, the basic idea is actually quite simple. Just consider two cases. One, again, a database where, two identical databases, except that one has John's information in it, the other does not have John's information in it. And any algorithm or mechanism that you are going to use can be considered differentially private if the output of that mechanism, the output of that algorithm over both of these databases is roughly equivalent. Okay, clearly not exactly the same, but it has to be roughly equivalent. And the reason why we claim this protects privacy is that someone who just looks at the output, what they get, is unable to figure out, oh, was the input the first or the second, which means they would not know whether or not John was part of the input that was used to compute this result. Okay, so it basically provides this plausible deniability for John, who can claim that, hey, I was never part of the result, never part of the input that was provided to this algorithm. And of course, in precise, if we go into this, there's a formal definition, there's a privacy parameter epsilon, and which has to be greater than 0, but smaller means more private. And what we really claim is that any mechanism M is epsilon differentially private if for every pair of neighboring databases, so X and Y that differ by one record, and for every possible output, if you will, the probability that you get that single or set of outputs for X and the probability that you get that, again, corresponding set of outputs for Y is bounded by e raised to epsilon. So is within a multiplicative factor of each other. And the smaller the epsilon, when epsilon becomes 0, as you can imagine, the probability is exactly the same, which means that, you've basically learned absolutely nothing, so to speak. But because this applies to all pairs of databases, if you will, in general. So this is a very nice sort of model. Again, this was created in 2006, so to speak. And if we sort of use this, we can guarantee to some extent output privacy, meaning just from the output, you would not be able to infer anything about people. So the question is this sufficient? Can I just go ahead and take SMC, take differential privacy, and say that I'm done? Does this solve the problem? Actually, not in theory, and also not in practice, as I'll just get to in sort of a few minutes. So by itself, this is great. This is a great starting point, but it's not sufficient. And I just want to give you one specific example of why, for example, this may not work. So in particular, say differential privacy won't work. And for that, I'm going to choose this example of outlier detection or anomaly detection, which again is a very, very standard data mining or data analytics task and has tons of applications in finance, healthcare, security, law enforcement, you name it, right? Finding anomalies or exceptions is really, really important. And it has lots and lots of different applications. So in particular, let's say you're trying to flag money laundering transactions in a privacy preserving manner. So first, why would you want to flag money laundering transactions? That's obvious, right? Because we want to know who is committing financial fraud. So the enforcement directorate, for example, would be very interested in knowing what's going on, just like the SEC over here, for example. But why privacy preserving? Because of course, for the people who are not doing anything wrong, we don't want that government, for example, or even banks have the ability to look at every single thing per se in terms of what we are doing. So again, I'll just show a very simple example where we are trying to do this identification using just the amount that is transferred. And you can think of the database as the number of such transfers that do actually occur. So here, anomaly, if you will, or a money laundering transaction is something that markedly deviates from other records. So something over here. Whereas normal would just be, say, sending money to your family or what have you, lots of different things over here. And accuracy clearly is mission critical to this application, if you will. We need to be able to identify the anomalies correctly. But we are going to focus on data-dependent definition of anomalies. So this point here is an anomaly because it's very different from all of the other data points. Clearly, if everything was the same or similar to that record, it would not be considered an anomaly. It would really be normal. And then we, of course, have a privacy puzzle that if there's high accuracy, there's no sort of privacy for outliers. We will know what the outliers are. But if there's no privacy for outliers, because the definition of outliers is data dependent, we don't have any privacy for the data defined normals as well. We basically know what would be regions of space which are quote unquote normal. And then the question is, okay, so what do we do? Does that mean that we have no privacy for anyone, regardless of whether you are an outlier or whether you are normal or somewhere in between? And the answer is, somehow our answer should not leak information about the normal records. We don't want to protect the anomalies because that is the required output, but we do want to protect the sort of normal records and be able to sort of do that. So I'm going to give you a very, very small overview of this. I won't go into details on this, but in particular, one notion of data-dependent anomalies are what are called beta R anomalies, which was defined by Nor and Eng in 1998, quite a long time ago. Which is a very simple notion. Basically, it just says, okay, take a record and look around it. If it has beta or fewer records with distance r within the sphere from it, then it is an anomaly. Okay, so basically, look around you. If you are alone and by yourself, you are an anomaly. If there are sufficient numbers of other records around you, you're not. And then I could just say, the anomaly detection function is, if I ask, is this kind of thing, let's go over the database, look at all of the different types of things that could happen. Just tell me all of the anomalies. That's the anomaly detection function. And here, typically, outliers are a very small fraction of the total records in the database. And small changes in the database don't sort of alter the record's outlying behavior. So databases as a whole are pretty sparse. This is standard, essentially this is what happens in real life anyway. So I just want to very, very quickly tell you why differential privacy has sort of poor accuracy in this particular space, right? So here are, and I'll just give you the intuition behind it. Here are two databases that are neighbors of each other. They are basically identical, okay? So the database is represented as a histogram. These are sort of the values which are being transferred. And the bar over here in the histogram is telling you how many such transfers occurred. And the two things are neighbors because they're identical. The only thing extra is that second last thing over there. And the anomaly detection function in this case says, oh, only this is an anomaly, whereas the anomaly detection function in this case says both of these are actually anomalies. Why is the other thing not an anomaly here? Because it's not present. If it's not present, it can't actually be an anomaly, correct? So actually, I'll ask even a much more simpler question, not what are all the anomalies, but is something an anomaly? So I'm just asking, is this kind of thing over here an anomaly for every database? So it's like someone saying, oh, if such and such a person was flying, given this values, is that an anomaly? So it's just a simple anomaly identification question, so to speak. Now, the problem is that when you use a guarantee like differential privacy, you're basically saying, oh, for a question like this, for every possible pair of databases, the likelihood of getting the same answer has to be roughly close to sort of each other. Now here, the answer in the first database, the answer is no, but in the second database, the answer is yes, which means whatever mechanism we are using, there's going to be an error either on the left or on the right. So in fact, we can show by the bound that the maximum error for one or the other has to be over 1 plus e raised to epsilon, which for small values of epsilon essentially means errors which are, close to 0.5 or even worse, which is almost the same, essentially as throwing a dice. And this means that we are going to make lots and lots of errors, not for the blue points, but basically for all of the anomalies and all of the empty regions in sort of space over here. And this, it doesn't matter what differentially private mechanism you use, even the optimal differential private mechanism is still going to have precisely this problem. It simply cannot be sort of avoided. And this outlier identification query, forget outlier detection, even the identification is pretty much impossible. So this problem basically exists as a whole, and this bound, so to speak, that we looked at, actually, it turns out it really depends on whether the query is existence independent or existence dependent, whether it depends on the existence of a particular record. And when things don't depend on a particular record, then you can still use differential privacy, no problem. You can go ahead and use that. But when the answer depends on the existence of a particular record, like in this case, is this thing an outlier? It depends on whether the record is present or not. Then you cannot use differential privacy. We are basically kind of just stuck. So as I said, the difference is just whether the answer is contingent on the absence or presence of a particular record. So basically, if you're just asking, is there a flu epidemic? How many outliers are in the data? We can still use differential privacy. But if you are saying, what are the outlier records? Is the record I an outlier? You cannot use differential privacy, not to give answers with any reasonable sort of utility. So we sort of came up with a principled approach to private outlier analysis. And the key thing there is to look at whether the query is existence dependent or not. And if it's not, then you can use DP. But if it is existence dependent, then we try to reduce it, to decompose it into a set of sort of queries, which hopefully can be existence independent. And then you can still use DP. But in the worst case, you have to use some notion of relaxed differential privacy. There is no real way around it. And the particular notion, basic generalizations and variants don't work in this space. But the particular notion that we sort of proposed is something called sensitive privacy, which I'm not going to go into in a lot of detail, but I'm just going to show you one picture, so to speak, which will give you the overall sort of intuition of this. So, and this is just the difference between what we have and what we want, okay? So on the left, what we have is differential privacy, where you actually have same privacy for all. So as you see here, you get exactly the same privacy for everyone, which is a good thing. But on the other hand, what happens is that your accuracy really drops. So this is, by the way, synthetic data. It's just a Gaussian, but it serves to illustrate the point that you get good accuracy for this mass in the center, but for everyone else, including the spaces where nothing is happening, you get horrible accuracy. It's very close to 0.5, which again is the same as tossing a coin. What we want is to somehow vary the privacy by outlierness, which means the huge majority of points in the center, everyone who is normal is getting the same privacy as in the old case. But as you are, acting in a more and more aberrant fashion, the degree of privacy you have reduces. And what this lets us do is then have accuracy at all of the points, except at the boundary where things are still a little bit difficult, but you can improve the accuracy in every other space, so to speak. And the interesting thing is, on the left, we have the optimal DP mechanism. On the right, we actually have achieved precisely this using a specific sensitively private mechanism, which I don't have sort of time to explain, but I just want to give you the key intuition that all we are doing is requiring privacy protection of every record that either is or becomes normal under a small change in the database. So basically protect everything that is normal or that can potentially be normal under some kind of small change in the database. So the first part is the same as differential privacy. The second part is the only sort of different thing. And this matches very well with what you want to do with anomalies, because anomalies are records that markedly deviate from other records. So small changes in the database should not change the status of an anomaly itself. It will protect all the normal or potentially normal records, just not the sort of anomalies. So I won't go into more details on sensitive privacy in particular, but I am going to talk a little bit about what is the infrastructure that we need, and especially from a cryptographic perspective, what does this imply? What do we need to be able to do? So going ahead, what do we need, so to speak? Because what we really need, what this sort of serves to show, is that you need a more nuanced view of privacy. You need sort of ways of accounting for privacy when we are basically saying how much information is being revealed. You need ways to explain privacy, what information is being revealed about you, visualizing what is actually happening, and exploring trade-offs with privacy. What would I be able to do given what information I'm willing to reveal, and so on. And the key point there is sort of the infrastructural support for privacy. So I think this is where it relates very well to existing sort of cryptographic infrastructures as well. If I want to work on distributed data, can I come up with good architectures where, again, I can make use, perhaps have this infrastructure already set up. There could be a few sites, what have you, which would basically turbocharge the possible analysis of data in this distributed sense while providing key guarantees of privacy, so to speak. So the next generation of privacy protecting systems actually will consider new architectures, incorporate diverse privacy models, and even take a socio-cognitive sort of approach to solving these problems. So if you remember the old why Johnny can't encrypt papers, just having technology is not sufficient. We really need to actually explain and to understand when things work and how they work and why they work, so to speak. So just one short point, changing the architecture in particular, where I think we can really create cryptographic infrastructure for this. I think what we are more and more going towards is this notion of collaborative computing, privacy preserving collaborative computing, where the input data, whether it comes from organizations or from individuals, would get split up between sort of multiple servers. These servers can be placed in trusted entities. For example, one could be in CDAC in Bangalore, another could be in CDAC in Pune. It could be within universities, what have you. I mean, there can be a few trusted entities, absolutely. And now, if the input data is split across all of this, you can still use sort of, garbled circuits, SNC approaches to sort of carry out computation over this information. And especially if we leverage the computing, leadership computing facilities and sort of the supercomputing power that we are, especially in terms of parallelization, that we are able to bring to bear today, I think it is possible to take existing functionalities and even come up with general purpose compilers that would let you then carry this computation out in general. A few other things, though, from the practice perspective. What if you want to enable privacy preserving sort of exploratory analysis? Can I get first cut, approximations of usefulness of data? As we know, in many cases, the real problem is not just, I need precisely this, encrypt that data, send it over, and we are done. We don't know what we need, and we are not sure what kind of cleaning or aggregation sort of needs to be done. So potential solutions in this space, which are not cryptographic, but the basic idea is that of creating synthetic data or sample data sets that sort of preserve the structure and semantics of the original data, but not exact values. That would give you some way of sort of preserving privacy while giving a first order sort of approximation of utility, if you will. And then making it work in practice. Again, differential privacy as a whole provides a nice framework for quantification, but there are a lot of assumptions. There are issues about data imputation and data sampling, and even data dependence, so to speak. So like if I use this for the census, if I'm just counting the number of children in single parent households, we can basically double count. There can be other problems that sort of occur in reality as well. So I think we do need more work. And again, I stress the point that we need infrastructural support where we basically specify prefixed values and very standardized protocols that are used for some of these things. And one particular thing, one last thing with respect to this, I talked about enabling meaningful control over data. I think there we still need traditional sort of security technologies or models, if you will, like access control. But we can couple that with sort of new technologies like machine learning and analytics to sort of automate policy configuration and management. So access control is still key. You're going to need that in order to ensure that proper control is put over data. But the question is, as evolving situations occur, can we automatically, without having to involve the security administrator in every single decision, is it possible to learn sort of data sharing policies or to explain current access policies or impact of changes and basically just make the job of the human the very experienced human in that situation a lot easier. Can we sort of do that to make this happen? So one last thing, I will very briefly talk about this, because this was very interesting and very relevant for all of us. We've all been suffering for the past 3 years through COVID in any case. But I wanted to talk about crowd sensing of data, and again infrastructural support, and how we can sort of make use of some of these technologies. So remember, at the start we had lots of problems in terms of testing for sort of COVID. So it was a very difficult problem to sort of detect COVID hotspots, especially to track them over time. Interestingly enough, this problem of detecting COVID hotspots was actually anomaly detection or outlier detection problem, because a hotspot is an anomaly. But the good thing here is that knowing whether something is a hotspot or not doesn't depend on any single record. So it turns out that you can actually use differential privacy in this space. Okay, so we don't need to worry about relaxed models. Differential privacy as a model will actually work in this space, as long as you collect the data also in a private way. So one problem though is that if you're asking these questions, so we actually came up with this app. This was again supported by NSF and NIH, which would let us guarantee privacy while crowd sensing. So you could ask questions. Let me go to Google Maps and just draw a region and say, oh, is this a hotspot? I could ask how many people reported feeling symptoms in the past 8 days in New York City. And I would get an answer. Then I could just basically look at everything, the whole thing on the map, or something really small, my particular block, if you will, and ask the question. The problem is, once you open up such an interface to anyone and everyone, an arbitrary number of such queries can be asked, differing in sizes and regions. So one query doesn't leak a lot of privacy, but all of them taken together is a huge problem that actually adds up significantly. So we could use the epsilon dp Laplace mechanism, but after n queries you lose privacy with every query essentially, and things are going to be horrible. We could have done something more different. You could have sort of this fixed grid, if you will, a very fine grid, if you will, and then you wouldn't have a privacy loss. But then guess what? Whenever you're looking for any region, now you have to aggregate over a whole bunch of these small regions, and you get errors from all of the underlying regions, so to speak. So you huge number of partitions, which requires huge space, but more importantly, it's very highly erroneous for queries for larger regions, which you absolutely need when you're looking for sort of hotspots. So what we ended up doing was a combination of techniques, which again, I don't have time and I won't go into, but I'm just going to briefly mention that the key idea here was sort of just to partition space. So spatial partitioning via a very well-known technique like quad tree. So you just take the unpartitioned space and just chop it into 4 quadrants and keep chopping up the quadrants while there is data in each of the quadrants. So I would just take this, which is everything, chop it up into 4 quadrants. And since there are only sort of more data in the top left and the bottom right quadrants, I further chop those up. And I create as many quadrants as sort of necessary to answer queries. But the other interesting part was, it's not just spatial data, it's spatio-temporal data, right? Because we care about the past 8 days or the past 14 days or what have you. So you need to sort of partition dynamically updating spatio-temporal data. So we have data at day 1, day 2, day 20, day 50, and so on. It's basically infinite time horizon, if you will, but a sliding window over that time horizon. So essentially for that, I'm not sort of going to go into this at all, but we have a very novel way of partitioning so that you don't create a tree at every single day, so to speak, and simply add up, again, have a privacy loss. You can actually minimize the privacy loss by being clever in the way of which days are you aggregating together to answer the maximum number of sort of queries. So we ended up sort of deploying this in reality in the world, through the Apple Play, through the Apple Store, through the Play Store as well, and so on. And we reported on this very recently in IEEE Intelligent Systems. But again, this was where you develop an app Now this part is secure. You are having the reporting of COVID-19 symptoms from individual users from their smartphones. You store the data in a secure database. And then in the background, every 24 hours, you get sufficient data, build these quad trees, and then update them. And now you can, when any query is posed, you can compute the queries via these quad trees and then go ahead and sort of answer this. So I would say you still need secure communication for the first part, but you need these underlying, differential privacy. And if you are distributing it, SMC technologies to sort of do the computation efficiently in the background as well before you're able to sort of answer these sort of queries in practice. And it gives you almost identical results with sort of guaranteed privacy. So, I'm just showing you a bunch of heat maps, if you will. One, the top level and the bottom level. One is in terms of the original counts, the other are the differentially private counts. And it turns out that they are pretty much privacy are, very straightforward in some sense that, we need to develop lightweight solutions that are robust to more powerful adversaries. Everyone just operates in sort of the semi-honest model at this point, where they expect people to follow the protocol. Does this always work in practice? And then how can we truly measure privacy along with utility so that exploratory analytics is truly possible? But more importantly, we are going to have this Internet of Things is happening, large sensory platforms, if you will, in places like this. How do we develop private, in environments like this, how do we develop private analytics? And can we optimize for things like computational complexity or even power use? Can we develop cloud infrastructures that minimize the use of power in this particular space? And I think over here, we have a lot of lessons to learn from sort of existing infrastructures like the PKI infrastructure as well. And the question is, how can we deploy these things in practice so that they may actually end up being used? So not just in a theory paper or in the lab, but really have it be used in practice. And for those of you who are interested in things like this, the National Institutes of Standards and Technologies, NIST in the US. So the US and UK government in collaboration recently came up with a privacy enhancing technologies prize. There's a competition that is ongoing where they're looking at two sets of data. One is financial crimes data. The other is basically pandemic forecasting. So again, health data, if you will. And the question is, again, in these sort of distributed use cases, what are the privacy challenges and what are the privacy enhancing technologies that we can use to sort of make this happen in a accurate but yet scalable and private way, so to speak. And then the last point over here, which doesn't have directly to do with sort of PKI or with crypto, but which we've all realized, purely technical solutions are great, but they don't work in practice. Again, like encryption has been around for forever, and we are still finding out that people have trouble using it appropriately. So can we develop socio-cognitive ways to improve privacy? And can we look at the interaction between privacy and other properties such as fairness? What are the roles that we have in order, to play so that we can make this happen in practice while ensuring all such properties are held appropriately. So with that, I will basically stop for questions. I hope I've not gone over time, but I did want to stop for questions.
Thank you, Jaideep, for an excellent talk on privacy. Any questions? Yeah. There is.
In context of the earlier panel discussion, there's a immense perceived risk about quantum computing in terms of the existing cryptography models. I'm just wondering, and maybe Dr. Jaideep, you mentioned heavily about analytics. So my question to you is, forget about QC, which is still fairly futuristic, but even the existing machine intelligence, has that been ever applied in terms of cracking the existing cryptographic models, even the most complex ones? We're not talking about brute computational power to crack cryptography. We're talking about intelligent computational power, Any effort in that direction which you're aware?
Yes, there are. Okay, so again, there has been classical cryptanalysis, if you will, and which goes well beyond that of sort of brute force attacks in any case. But coming back to your question, absolutely, there is in fact a quite a bit of work in this space. So even for example. When you're thinking of differential cryptanalysis, you can think of timing attacks and so on. Now, there is the use of basically large scale computational power and data analytics technologies in this space, simply because, depending on the particular model, let's say you have a NCPA sort of system that you have to break, you still have sort of Oracle access to it. You can collect a lot of data points and then essentially figure out the right queries to ask. So there is some degree of work along these lines, and especially even from a hardware security perspective in terms of finding vulnerabilities against this. Yes, absolutely. I mean, this is a burgeoning area of work, if you will. The one thing I have not heard of yet is the sort of use of, since people like to put buzzwords together, I still haven't heard of anyone saying, oh, let's create a neural network to sort of encrypt or decrypt data on the fly. And that doesn't make any sense. And that's just a joke, but regardless. But yes, absolutely. There is the use of sort of modern ML technologies to sort of target this, if you will, or to improve this. I'm not sure if that completely answers your question, but I would be happy to discuss it afterwards as well.
No, sure, it does answer. I mean, in fact, I would just say that that is probably a more realistic and imminent threat, if at all, to these cryptographic models than a very perceived decades down the line quantum computing based threat. Anyway, it was just a thought.
The differential privacy, in my view, it is applicable for a different class altogether, in a sense. Okay, so for example, if you have sensitive attributes which are not real or integer, adding error is
Right.
not a easy thing. And if you in fact, if you have many quasi attributes, how would you arrive at a probability distribution on the sensitive attributes so that the differential privacy can add appropriate error? That is not a easy thing. Actually, anomalies is not a thing that the differential privacy is going to handle, or it should not handle. And the classical anonymity, diversion, closeness, where you use a lattice-based kind of a thing, where you can suppress or not suppress, it is left to you, kind of a thing, or the other. So in a sense, I think there should be a good categorization, like even Apple and Google use differential privacy, but for they use for a limited period of time, one does not know how much privacy is being given to a trusted party of Apple and Google. But Apple and Google are the ones who are trusted agents of the world, so they have all the data. So you can't question that kind of a thing or the other. And so, and that is the basic thing or the other. And if you want to find anomalies, the only way, in my opinion, privacy can be preserved is homomorphic encryption. Hopefully, Craig's new company is going to give solution without encryption. I do not think utility and all these things can be preserved. But however, in my opinion, if you have a statistical database kind of a thing, like a census data and all the other things, for which I think otherwise you gave counterexamples for which there is a case against differential privacy being deployed by US Census Bureau. All of the examples are given there, kind of a thing. Thank you. And then we look forward to your new privacy model to see how it could be used, and in the COVID kind of a thing are there. Thank you, Jaideep, for giving your time and then giving. Thank you.
Thank you. Thank you very much.